Hello! This is a 45-minute deep dive into late interaction theory and application. It has several lessons based on research papers for ColBERT and ColBERT v2 from a few years ago, as well as the Wholembed v3 release announcement from yesterday. I will start with some background on sparse lexical matching with BM25 and dense single-vector embedding, and then focus on the more advanced and powerful concepts of multi-vector late interaction. Welcome to today's lesson on the bedrock of modern information retrieval, traditional keyword search. If you've ever wondered how search engines instantly pinpoint the right document, you're about to pull back the curtain on the industry standard ranking function, BM25. In this session, we'll break down the mechanics of sparse lexical matching, decode the BM25 formula itself, and explore both the limitations of this approach and why it remains a vital, relevant tool in today's tech landscape. Whether you're building search systems or just curious about how data is organized, this is a foundational skill that will change how you look at search forever. Let's dive into the mechanics of sparse lexical matching. At its core, traditional keyword search relies on identifying exact or near exact matches of the words or tokens within your query. We call this sparse retrieval because it focuses on the presence or absence of specific terms, rather than trying to map out the deeper continuous meaning behind them. The gold standard for this type of search is a model called BM25. It's a probabilistic tool that ranks documents based on how frequently your search terms appear, but it improves upon older methods by refining how it weighs those occurrences. It does this through two essential concepts, term saturation and document length normalization. First, let's talk about term saturation. In simpler systems, if a keyword appeared 100 times, the score would be 100 times higher. But BM25 recognizes that relevance hits a point of diminishing returns. Once a term appears a few times, a document is clearly about that topic. Seeing that word 50 more times doesn't make it 50 times more relevant, so the model caps the benefit of those extra mentions. Second, we have document length normalization. Think about a long, sprawling article versus a short, concise post. A very long document is naturally more likely to contain search terms simply by chance, not necessarily because it's a better match. BM25 accounts for this by penalizing overly long documents and rewarding shorter, more focused pieces that get straight to the point. By balancing these two factors, BM25 provides a much more nuanced approach to finding exactly what you're looking for. At the heart of modern search engines lies a powerful mathematical framework called BM25. It determines how relevant a document is to your search query by calculating a total score, which is the sum of scores for each individual term in that query. To understand how it works, think of it as a balance of three primary components. First, we have the inverse document frequency, or IDF. This acts as a filter for importance. It gives higher weight to rare, meaningful words while penalizing common filler words like the or is, which don't help much in finding specific content. Second, we look at term frequency, represented by f of qd. This measures how often a term appears in a specific document. However, BM25 doesn't just assume more is always better. It uses a parameter called K1 to control term saturation. This means that after a certain point, seeing the same word repeatedly stops adding significant value to the relevance score. Finally, the formula accounts for document length. By comparing the length of a specific document to the average length across your entire collection using a parameter called b, the algorithm adjusts for bias. Without this, long documents might unfairly dominate results simply because they contain more words. By elegantly weaving together term importance, frequency, and document length normalization, BM25 provides a nuanced, highly effective way to rank the documents that matter most to your search. While BM25 is a reliable workhorse for search, it has a significant blind spot. It doesn't actually understand what your words mean. Because it treats documents like a simple bag of words, it struggles with the nuances of human language. First, there is the problem of synonyms. If a user searches for the word automobile, BM25 will completely ignore documents that only use the word car. Even though they mean the exact same thing, the system sees no matching terms, and therefore it returns nothing. Then we have to deal with polysemy, the fact that many words have multiple meanings. Think of the word bank. If you search for it, BM25 can't tell if you're looking for a financial institution or a riverbank. It simply retrieves every document containing the word, leaving you to sift through irrelevant results. Finally, BM25 lacks an understanding of conceptual relationships. It doesn't know that dogs and cats are types of mammals. Because these terms don't match the query string lexically, the system fails to make those logical connections. In short, while BM25 is great at counting words, it often misses the actual intent behind the search. So, if there are newer, more advanced methods out there, why do we still rely on BM25? The answer comes down to three main strengths: reliability, speed, and precision. First, there is the issue of interpretability. When a user asks why a specific document appeared at the top of their results, BM25 makes that easy to answer. We can point directly to the specific keywords that triggered the match, which is a huge advantage for debugging and transparency. Second, BM25 is incredibly efficient. Because it utilizes inverted indexes, essentially a straightforward map of terms to document IDs, it can retrieve results from millions of records near instantaneously, and it does so without the heavy computational power required by deep learning models. Finally, BM25 serves as an essential performance baseline. In many professional fields, like looking up a specific product serial number or a precise legal citation, you don't need semantic nuance. You need an exact lexical match. When you want the search to be literal, BM25 is often exactly what the user needs. Because of this, modern search systems are moving toward what we call a hybrid search. By combining the exact keyword matching power of BM25 with the intent awareness of modern vector-based AI, we can build systems that give us the best of both worlds, the precision of keywords and the intelligence of semantic search. Welcome to this lesson on the power of single-vector semantic search. Today we're bridging the gap between human language and machine intelligence. We'll start by exploring the core concept of semantic embeddings, then walk through the encoding process that turns simple queries into meaningful vectors. You'll discover why single vector retrieval is a game changer for speed and accuracy, and we'll wrap up by tackling the inherent limitations you might face in practice. Get ready to master the technology that makes modern search smarter than ever. At the heart of modern search is the concept of a semantic embedding. Unlike traditional search methods that just look for matching keywords, semantic search aims to understand the deeper context and intent behind your query. But how does a computer actually understand language? It does this by transforming text into a high-dimensional vector space. Think of this as mapping words, sentences, or entire documents into a list of floating-point numbers. These numbers capture the semantic essence of the content. This transformation is usually performed by a deep learning model, like a transformer-based encoder, which ensures that pieces of content with similar meanings are positioned physically close to each other in this multi-dimensional space. Once we have these vectors, we need a way to measure how close they are. We do this by calculating the distance or the angle between them. The most common way to measure this is called cosine similarity. Essentially, we take the dot product of two vectors, let's call them A and B, and divide that by the product of their magnitudes. The result is a value between -1 and 1. When the cosine of the angle is close to 1, the vectors are pointing in nearly the same direction, which tells us that the two pieces of text are highly similar in meaning. At the heart of modern search is the encoder. You can think of the encoder as a sophisticated, pre-trained neural network that acts as a translator. It takes a sequence of text, whether it's a short question or a lengthy document, and compresses it into a single fixed-length string of numbers known as a dense vector. In this one-vector paradigm, even massive documents are distilled into a compact representation, typically consisting of 768 or 1,536 dimensions. This compression is what makes large-scale searching possible. It transforms a complex linguistic task into a streamlined mathematical one. Here is how it works in practice. When you search for something like how to fix a leaky kitchen faucet, the encoder instantly converts that query into a vector. Because your entire database has already been pre-processed, with every document converted into its own unique vector, the system doesn't need to read through the text again. Instead, it performs a rapid calculation to find which stored document vector is mathematically closest to your query. By focusing on the proximity of these vectors, the system can identify the most relevant information with incredible speed and efficiency. Single-vector semantic search is a major leap forward from the legacy search systems of the past. It offers three primary advantages that make information retrieval more intelligent and efficient. First, it excels at handling synonyms and paraphrasing. In traditional keyword search, if you search for automobile maintenance, you might miss critical documents that simply use the words car repair. Semantic search solves this by recognizing that automobile and car exist in the same conceptual space, ensuring you get the right results even when the phrasing differs. Second, these systems possess true contextual understanding. Modern encoders can handle polysemy, or words with multiple meanings, by analyzing the surrounding text. Take the word bank, for example. The system can distinguish between a riverbank and a financial institution by looking at the context, mapping the term to the correct location in the vector space. Finally, there is the advantage of scalability. Because documents are pre-converted into vectors, search engines don't need to scan every single record line by line. Instead, they use algorithms called approximate nearest neighbors to navigate millions of records in mere milliseconds. This means you get lightning-fast results even across massive data sets. While the single-vector approach is powerful, it's important to understand that it isn't a universal solution. When we compress complex information into one vector, we're essentially creating a high-level summary of the entire document. This creates what we call an information bottleneck. If a document covers 3 distinct topics, a single vector might just provide an average meaning, missing the specific details needed for granular queries. This limitation often leads to 2 major failures. First, it struggles with rare terms. If a user searches for a specific technical model number or a unique medical term, a dense model that hasn't seen that term during training might fail to match it entirely. Second, it often hits a wall with entity overlap. Because the vector represents the general topic, the system might treat 2 documents as identical, even if one is a contract for company A and the other is for company B. It loses the critical detail that makes them different. Because of these hurdles, many production-grade systems now rely on hybrid search. By combining the conceptual intelligence of dense vector search with the precision of traditional keyword-based sparse search, we get the best of both worlds. We then blend these signals using a method called reciprocal rank fusion. This approach ensures that a search engine is not only smart enough to understand the big picture of a user's request, but also precise enough to land on the exact facts and entities that matter most. Welcome to our deep dive into the world of neural information retrieval. Today we're exploring the evolution of search, moving beyond simple keywords to the cutting-edge power of AI. We'll start by uncovering the limitations of traditional search before diving into how deep learning is transforming the field. You'll learn how to balance computational costs, discover clever strategies like late interaction to boost efficiency, and get a glimpse into the future of semantic search. Get ready to master the technology that is fundamentally changing how we find information. Let's begin. Before the rise of modern neural models, search systems relied on lexical matching. Think of these as systems that scan for exact word overlaps. If you use tools like term frequency inverse document frequency or the popular BM25 algorithm, the system simply assumed that the more shared terms a query and a document had, the more relevant the document must be. But this approach faces a significant hurdle known as the semantic gap. Because these systems only look at the literal words, they struggle with 2 major linguistic challenges, synonymy and polysemy. Synonymy happens when different words carry the same meaning. If you search for an affordable laptop, a traditional system might completely miss a document titled cheap notebook computer because to the machine, the words don't match. Then there is polysemy, where the same word has multiple meanings. A search for bank leaves the system guessing. Is it talking about a financial institution or the grassy side of a river? While developers tried to improve these systems with techniques like query expansion or pseudo-relevance feedback, they were ultimately limited by that same rigid dependence on exact word overlap. They were looking at the words, but they weren't truly understanding the meaning. Welcome to the world of neural information retrieval. At its heart, this approach uses deep learning, specifically transformer models, to rethink how we match searches to content. Instead of just looking for matching keywords, neural IR represents queries and documents as dense vectors in what we call an embedding space. Think of this as a vast, multidimensional map where related concepts naturally cluster together. A major turning point for this field was the introduction of BERT. Unlike older systems that analyzed words in isolation, BERT looks at entire sentences at once. Because it processes text bidirectionally, it captures the nuanced relationships between words, allowing it to truly grasp the context of a search. When we use models like BERT in an IR context, we transform text into these deep semantic embeddings. The magic happens when we compare them. If a query vector and a document vector are positioned close to each other in that embedding space, the model identifies them as semantically relevant. This is powerful because it allows a search engine to find a document even if it doesn't share a single word with the original query. To determine just how close they are, we calculate their similarity using a mathematical formula known as cosine similarity. In plain terms, we calculate the dot product of the query and document vectors, and then divide that by the product of their individual magnitudes. This gives us a precise measurement of their directional alignment, effectively quantifying how well the document answers the user's intent. Now let's talk about the computational trade-off. While neural models offer incredible accuracy, they come with a significant cost: massive computational overhead. Think of traditional keyword-based search like using an index at the back of a book. It's incredibly fast because it's just a simple dictionary lookup. Neural models, on the other hand, are much more intensive. To understand a piece of text, they have to push it through complex, multi-layered neural networks. This leads us to the inference bottleneck. When you're dealing with millions of documents, running a heavy model, like BERT, over every single one for every search query just isn't feasible. If one search takes a certain amount of time, doing that for 1 million documents makes the total time climb far too high. For real-time applications, this approach is simply too slow. This leaves us caught in what we call the latency accuracy paradox. You can choose higher accuracy, which requires those deep transformer-based encoders, or you can prioritize lower latency, which requires sticking to those faster, traditional search methods. Finding the balance between these two is one of the biggest challenges in modern information retrieval. To handle the massive computational strain of searching through millions of documents, researchers have shifted away from processing everything on the fly. Instead, modern systems decouple document processing from query processing, enabling us to use powerful index-based search methods. This brings us to dense retrieval and approximate nearest neighbor search. Rather than comparing every single document to a query at runtime, we pre-index the entire collection. Offline, we feed every document through a BERT-based model to create a static database of vectors. Then, when a user enters a query, we use an algorithm like HNSW or FAS to retrieve the most relevant documents in milliseconds, simply by finding vectors that are geometrically close in space. However, compressing an entire document into a single vector can sometimes lose nuance. This is where late interaction models like ColBERT come in. Unlike standard models that boil a document down to one point, ColBERT keeps the individual embeddings for every token. This allows for a much more detailed, fine-grained interaction between the words in a query and the words in a document. By combining this level of precision with optimized search indexing, we can maintain high accuracy without sacrificing the speed needed for real-time applications. Now that neural information retrieval has set a new standard for search engines, our focus is shifting toward efficiency. While semantic understanding is now a baseline expectation, the field is evolving to make these powerful models faster and more lightweight. There are three major trends currently leading this charge. First is model distillation. Think of this as teaching smaller student models to mimic the performance of their larger counterparts. By doing this, we keep the intelligence of a massive model while significantly reducing the cost of running it. Second is quantization. This involves reducing the precision of our vector data, for example, by using 8-bit integers instead of the standard 32-bit floating point numbers. This simple adjustment drastically shrinks the size of our search index and speeds up the time it takes to compare results. Third is the rise of hybrid search. This approach combines the traditional keyword matching precision of BM25 with the deep semantic relevance of neural models. By merging these two strategies, we ensure that search results are both accurate and contextually meaningful. Looking ahead, as hardware like TPUs and optimized GPUs become more widely available, the computational overhead of neural search will continue to fall. Ultimately, this means that even smaller scale applications will soon have access to the same sophisticated, semantic-aware search capabilities that define the cutting edge today. Welcome to this lesson on the power of multi-vector representation. If you've ever felt that standard text embeddings lose too much detail when summarizing a document, you're in the right place. Today, we're moving beyond the limitations of single vector models. We'll explore the bag of vectors approach, uncover the unique benefits of multi-vector architecture, and look at the practical implications for building more intelligent systems. Get ready to unlock a deeper, more nuanced way for machines to understand language. To understand why multi-vector representation is such a game changer, we first need to look at the limitations of standard single vector embeddings. Think of it like trying to summarize a 60-page legal contract into a single sentence. No matter how hard you try, you're inevitably going to lose the specific clauses, the exact dates, and the names. Standard embedding models do something very similar. They take the individual vectors for every word in a document and perform a mathematical operation, like averaging them, to create one single vector that represents the overall theme. This is known as mean pooling. The problem is that this process creates a massive loss of precision. By collapsing an entire document into one average point in space, you lose the ability to perform high-precision searches. If a user queries a specific technical term or a unique name, that information often gets washed out by the more frequent generic words in the text. While a single vector is great at capturing the general gist of a document, it simply lacks the granularity required for tasks where exactness is the priority. In short, you gain a broad overview, but you lose the fine-tuned detail. Let's explore the bag of vectors approach, a method that shifts how we represent information from a single, broad overview to a highly granular, detailed map. In standard models, a document is compressed into one single point in space. But in a multi-vector framework, the model processes the document and generates a unique, distinct vector for every single token. This is a powerful way to preserve semantic granularity. Because each word has its own vector, the system can distinguish between different meanings based on context. For instance, if a document uses the word apple to refer to the fruit and later uses it to refer to the technology company, the model generates two unique vectors that capture those distinct definitions. So how does this actually function? Think of it less like a single point and more like an index or a bag of vectors. When you search for information, the system doesn't just compare one point to another. Instead, it compares the tokens in your query against the entire collection of vectors in that document. By matching specific components of your query to specific parts of the text, The model can surface results based on precise, meaningful details, rather than relying on a holistic score that might miss the bigger picture. Moving to a multi-vector architecture offers a major upgrade for retrieval augmented generation and semantic search. The primary advantage is enhanced relevance. By storing vectors at the token level, the system uses what we call late interaction. This means it calculates connections at the very end of the process, allowing it to pinpoint specific keywords or phrases that matter most, even if the overall theme of the document doesn't perfectly align with the query. This is especially powerful when dealing with complex multi-topic documents. Imagine a long research paper covering 3 distinct subjects. A traditional single-vector model would essentially try to average those topics together, which often dilutes the meaning and makes it harder to find specific information. A multi-vector model, however, keeps the information for each subtopic distinct. Because the tokens remain individually accessible, the system can retrieve that document based on a query about just one of those topics, rather than needing to match the broad average theme of the entire paper. It's a much more surgical approach to finding exactly what you need. When we move from standard vector databases to multi-vector representations, we fundamentally change how we handle data. Instead of condensing an entire document into a single vector, we store one vector for every individual token. This creates a significant shift in storage requirements. If a document contains 500 tokens, your storage needs grow by that same factor. Because you are dealing with such a high volume of data, you need a much more robust infrastructure and smarter indexing strategies to ensure that retrieval remains fast and responsive. You will also notice a change in the computational load. During retrieval, the system has to perform far more complex mathematical operations to compare your query against that expanded set of document vectors. While this is more demanding on your hardware, the payoff is substantial. For applications where precision is everything and capturing subtle semantic differences can make or break the user experience, the added depth of multi-vector models is well worth the investment. Welcome to our deep dive into the MaxSim operator. In the world of neural search, capturing the true meaning of a document is everything. Today, we're moving beyond traditional global vectors to explore the power of token-level interaction. We'll break down how the MaxSim calculation actually works, why it offers such a massive performance boost over standard methods, and walk through a practical step-by-step scenario to bring these concepts to life. Finally, we'll cover key considerations for your own implementation. Get ready to transform how your systems understand relevance. Let's get started. To truly grasp how MaxSim works, we need to change how we think about search. Forget the idea of a document as just a single, static point in space or a simple bag of words. Instead, visualize both your query and the document as long chains of individual tokens, with each token translated into a unique high-dimensional vector. Think of it like this. If your query has a certain number of tokens and your document has its own set, we aren't just comparing one overall summary to another. We're actually looking at the relationship between every single query token and every single document token. The MaxSim operator is based on a simple but powerful premise. A query token is considered satisfied if it can find at least one strong match somewhere within the document. We don't want to just average those similarities or add them all up because that would dilute the signal. Instead, for every individual token in your query, we hunt for the maximum similarity score it can find anywhere in the text. By focusing on these individual best matches, MaxSim allows us to capture the nuances of language that a traditional high-level summary might miss. How exactly does the MaxSim operator work? At its core, the math is elegant because of its simplicity. Think of your query as a collection of individual vectors, where each one represents a specific term or concept. Your document is also a collection of vectors, representing its own content. To find the relevance, we compare every query term against every document term using cosine similarity, which measures how closely the meanings align. For each individual token in your query, we look through the entire document to find the single best match, the highest similarity score available. That is the max part of MaxSim. Once we have identified the strongest match for every single query token, we add those maximum scores together to get our final total. This approach is powerful for 2 reasons. The inner operation ensures that we are always capturing the best possible semantic match for each specific part of your query. Then the outer operation aggregates those matches, ensuring the total relevance score reflects how well the document covers every important concept in your search. It is a precise, token-by-token way to determine exactly how relevant a document is to your specific request. Why does MaxSim outperform traditional global vector methods? To understand this, first think about how standard retrieval works. Most models compress an entire document into one single vector. That works for broad topics, but it often struggles with complex queries that need specific, multifaceted answers. That's where MaxSim changes the game. First, consider the issue of specificity. If a user searches for best noise-canceling headphones for travel, a global vector might capture the general idea of audio gear, but it often misses the nuance. MaxSim takes a more surgical approach. It effectively breaks the search down, looking for a match for noise canceling, a match for headphones, and a match for travel individually, ensuring every part of the request is accounted for. Second, MaxSim is much better at mitigating noise. Documents are often long and full of irrelevant filler. By calculating the maximum similarity between tokens, the model essentially ignores the background noise and focuses only on the hits, the specific words that actually matter to your query. Finally, there is the advantage of explainability. Because MaxSim operates at the token level, it's much easier to interpret the results. You can trace exactly which parts of a document contributed to the relevance score. This creates a clear, transparent link between what the user asked and why the system chose a particular result. By shifting from a single global summary to a token-by-token comparison, MaxSim delivers the precision that modern search demands. To see how this works in practice, let's look at a quick example. Imagine a user searches for the phrase fast car, which gives us two query tokens, fast and car. Now, suppose our document contains the sentence, "The vehicle is incredibly speedy." In a traditional keyword search, this might not be a perfect match. But with the MaxSim operator, we look at the semantic relationship between those words. First, we take the query token fast and compare it against every word in our document. The model recognizes that fast and speedy are semantically similar, giving us a score of 0.85. Next, we do the same for the query token car. We compare it to the words in our document and find a strong connection to vehicle, resulting in a similarity score of 0.90. To get our final result, we add those maximum scores together, 0.85 plus 0.90, giving us a total MaxSim score of 1.75. By using this method, the system successfully recognizes that fast car is highly relevant to the vehicle is incredibly speedy, even though the document doesn't contain a single one of the original search words. It's a powerful way to bridge the gap between human intent and the actual words on the page. While MaxSim is a powerful tool for matching queries to documents, it does come with practical challenges. Because the technique involves comparing every query token against every document token, the computational cost can climb quickly as documents get longer. To manage this, efficiency is key. For massive documents, building a full similarity matrix can strain your system's memory. To work around this, developers often use inverted indices or pruning techniques to narrow down the most relevant tokens before performing the calculation. You also have flexibility in how you aggregate your results. Depending on your goals, you might choose to average your similarity scores instead of summing them, or apply weights to prioritize specific query tokens, like focusing on important nouns rather than common stop words. Finally, keep in mind that the quality of your results hinges on the quality of your embeddings. We strongly recommend using contextual embeddings, like those from BERT-based models, rather than static word embeddings. By understanding a word based on the specific context of the surrounding text, these models provide the depth needed to make MaxSim truly effective. Welcome to this lesson on achieving efficiency through offline pre-computation. In today's world of high-speed search and AI, delivering instant answers is a massive technical challenge. In this session, we'll explore how to overcome the bottleneck of real-time encoding costs. We'll look at the clever strategy of separating query encoding from document interaction, and dive into how dual encoders or biencoders serve as the backbone for this architecture. By the end, you'll understand how these techniques drastically improve system scalability, allowing you to build faster, more responsive retrieval systems. Let's get started. To understand why we rely on pre-computation, we first need to look at how modern neural retrieval systems function. At their core, these systems use deep learning models like transformers to map both your search query and our document library into a shared mathematical space. If we tried to do this entire process in real time, every time a user hit the search button, we'd run into a major scaling problem. First, we would have to feed every single document in our collection through the neural network. Then we'd have to calculate the similarity between the user's query and every one of those resulting vectors. Think about the math. If you have millions of documents, the time it takes to process the collection is equal to the number of documents multiplied by the cost of encoding each one, plus the cost of those millions of similarity comparisons. When your collection reaches millions of items, this approach becomes incredibly slow. It's simply impossible to achieve the sub-second response times that users expect today. That is exactly why we move these heavy computations offline, turning a real-time bottleneck into a manageable, pre-computed search experience. To build high-performance retrieval systems, we rely on a core philosophy, decoupling the document processing from the query processing. Instead of scanning a massive library every time a user asks a question, we pre-process the entire collection into an indexed database. This happens in two distinct stages. First, we have the offline phase, or indexing. Here, we pass every document in our collection through a neural encoder, which transforms the text into a fixed-length vector, essentially a numerical signature of that document's meaning. These vectors are stored in a specialized database, like an approximate nearest neighbor index. Because this happens offline, we can use massive parallel computing power to build this index without ever slowing down the user. Then we have the online phase. When a user submits a query, we only need to perform one task, encode that single query into its own vector representation. Once we have that, we perform a search to find the document vectors that are closest to our query vector. Because we've already done the heavy lifting ahead of time, the computational cost at query time is extremely low. It's simply the cost of encoding one query plus the time it takes to perform a fast, sublinear search through our index. By separating these two steps, we transform a potentially massive search problem into a lightning-fast retrieval process, making it possible to serve high-performance results in real-world production environments. To make offline pre-computation work, we need an architecture that allows for independent processing. This is where the dual encoder, or bi-encoder, comes into play. Think of a dual encoder as a system with two separate neural network branches, one dedicated to your search query and another dedicated to your documents. This setup is powerful for two main reasons. First, it enables independent processing. Because the document branch acts entirely offline, we can generate document vectors once and store them. They don't change regardless of what the user types into the search bar. Second, both branches map their inputs into a shared d-dimensional vector space. By forcing the query and the document into the same mathematical space, the dot product between the query vector and the document vector becomes a meaningful measure of relevance. By keeping these pathways separate, but anchoring them in a shared embedding space, we ensure that the heavy lifting done on the documents remains perfectly valid and reusable for any query that comes along. When we shift to offline pre-computation, we fundamentally change the nature of our system. We move away from heavy real-time processing and turn our search architecture from a compute-bound task into one that is bound by memory or input-output speed. This is a game changer for scalability because these constraints are much easier to manage. First, consider caching. Because our document vectors are static, we don't need to recalculate them. We can store them directly in high-speed RAM or distribute them across a cluster of GPUs. This turns a complex search operation into a nearly instantaneous lookup. Second, we gain flexibility through asynchronous updates. If your corpus grows and you need to add new documents, you don't have to freeze your system. You can simply encode those new items in the background and fold them into the index incrementally, keeping your service running without a hitch. Finally, pre-computation allows us to utilize powerful indexing techniques like product quantization or hierarchical navigable small world graphs. These methods slightly trade off a tiny bit of precision for a massive leap in retrieval speed. It's exactly how systems can scan through billions of documents in a fraction of a second. By mastering this separation between query encoding and document interaction, you move beyond just building a search engine. You're creating a robust, high-performance system capable of meeting the speed and scale demands of the modern web. Welcome to this deep dive into the world of high-dimensional vector search. While multi-vector models like ColBERT have revolutionized information retrieval, they come with a massive storage and speed challenge, the multi-vector bottleneck. In this lesson, we're going to master the solution. We'll start by building a foundation in product quantization, then move into the power of residual compression to refine those approximations. We will walk through how to implement these techniques at scale and finally analyze the critical balance between efficiency and accuracy. By the end, you'll have the tools to make your retrieval systems faster, leaner, and incredibly effective. Let's get started. When we talk about traditional search methods, they usually represent an entire document as a single fixed-length vector. While this is efficient, it forces us to collapse all the nuance of a document into one spot. Multi-vector models solve this by creating a collection of embeddings for a single document, one for every token or segment. This allows for much more sophisticated, late interaction scoring. However, this comes with a catch, the storage multiplier effect. If a single vector model uses a certain number of dimensions, a multi-vector model multiplies that requirement by the number of segments, which we'll call n. If you're working with a collection of billions of documents, the math changes quickly. While a single vector approach scales linearly with the number of documents and their dimensions, the multi-vector approach multiplies that entire requirement by n. Since n can easily range from 32 to over 200, your storage needs can balloon to tens of terabytes. At that scale, it becomes incredibly difficult to keep these indices in memory for the rapid search performance we need. Before we dive into residual compression, we need to cover the cornerstone of vector compression, product quantization, or PQ. At its core, PQ is a strategy for shrinking high-dimensional data. Imagine you have a long, complex vector of size d. Instead of trying to compress that entire vector at once, PQ breaks it down into m smaller, distinct subvectors. For each of these subvectors, we use a pre-computed codebook to find the closest match, or centroid, and then replace the original float values with a simple integer, an index pointing to that centroid. This process is incredibly efficient for memory. For example, a 128-dimensional vector, which would normally take up 512 bytes using standard float32 precision, can be crushed down to just 16 bytes. That is a 32 times compression ratio. However, there is a trade-off. Because we are approximating our data with these indices, we introduce quantization error. In practice, this means that while PQ saves a massive amount of memory, it can sometimes lead to a drop in the precision of our search results. Understanding this limitation is the first step toward mastering more advanced compression techniques. When it comes to scaling multi-vector models, standard techniques like product quantization often lose too much detail. To fix this, we use a process called residual compression. Think of it as a two-stage approach that doesn't just settle for a rough approximation, it actively refines it. The secret lies in the residual. When we create a coarse approximation of a vector, there is always some information lost in the process. We define this loss mathematically as the residual, the original vector minus that coarse centroid. Instead of just saving the coarse version, we take that remaining gap and quantize it using a second, finer-grained codebook. By capturing that missing detail, we effectively store the nuance that the first pass left behind. When it's time to search, the system performs a two-stage decoding process. It reconstructs an estimate of the original vector by simply adding the coarse centroid to the refined residual. By dedicating our storage capacity to these residuals, we reach a much higher level of accuracy. This allows us to keep the high-fidelity representation of multi-vector models while drastically shrinking their memory footprint, ensuring that retrieval quality stays high even as we scale. When we scale residual compression to datasets containing billions of vectors, our engineering focus shifts. The goal is simple: maximize the number of queries processed per second while keeping the reconstruction of those vectors lightning fast. The effectiveness of this process starts with the quality of our centroids. In production, we approach this in two ways. First, we use large-scale k-means clustering on a representative sample of the data. This ensures our initial codebook is a perfect map of the underlying vector distribution. Second, we use adaptive bit allocation. Instead of treating every dimension equally, we assign more bits to the residuals that carry higher variance. By focusing our precision on these more informative dimensions, we maintain high fidelity where it matters most. However, the real challenge happens at search time. Calculating the reconstructed vector by adding a centroid to its residual for every candidate is too slow. To solve this, we optimize our memory layout and retrieval. Instead of recalculating distances from scratch, we use pre-computed lookup tables. These tables store pre-calculated distances between queries and centroids, allowing the system to retrieve results instantly. Finally, we leverage SIMD parallelism. By using single instruction multiple data processing, our CPUs can perform complex addition and distance calculations across thousands of vectors in a single operation, keeping our retrieval systems both massive in scale and incredibly fast. The true power of residual compression lies in the balance it creates, what we call the Pareto frontier. By carefully tuning how many bits we allocate to coarse centroids versus residual codebooks, system designers can find the perfect sweet spot between saving space and maintaining search precision. When we scale up to billions of data points, the practical gains are transformative. First, there is a massive reduction in your memory footprint, typically between 16 and 64 times smaller than the original. This allows the entire index to live comfortably in RAM, which eliminates the bottleneck of slow disk operations and keeps latency incredibly stable. Crucially, this doesn't come at the cost of quality. You can expect to keep your recall performance within just 1 or 2% of an uncompressed baseline. Ultimately, residual compression shifts the multi-vector approach from a research luxury into a high-performance engine for real-world information retrieval. Welcome to today's lesson on the future of information retrieval. We're moving beyond simple text to explore the powerful world of omnimodal and multilingual capabilities. In this session, we'll discover how late interaction architectures are evolving to handle audiovisual data and bridge the gap between different languages. We'll break down the core system architecture, see how these models achieve cross-modal alignment, and explore the real-world impact of this technology. It's an exciting leap forward in how machines understand our world. Let's dive in. Traditional retrieval models often struggle because they try to compress an entire document into a single compact vector. While efficient, this approach sacrifices nuance and detail. Late interaction models, like ColBERT, take a smarter approach by keeping document information at the individual token level. This allows the system to hold off on deciding what is relevant until the very final stage of the matching process. To understand how this works, think of both the query and the document as collections of individual points in a shared mathematical space. We represent a query as a set of embeddings and a document as another set of embeddings. To find the relevance score, we use what's called a maximum similarity operation. For every single element in the query, we scan the document to find the most similar counterpart, and then we add up those highest scores to get our final total. This framework becomes incredibly powerful when we move beyond text. In omnimodal retrieval, the document embeddings don't have to be limited to words. They could represent specific frames in a video, segments of an audio track, or regions of an image. As long as our encoder can map these diverse media types into that same shared vector space as our text query, the late interaction framework can find deep, nuanced connections between completely different types of data. How do we bridge the gap between human language and multimedia? To make audio and video searchable, we have to align these non-textual formats with text. We achieve this through a process called contrastive pre-training, where models are trained on massive datasets pairing video and audio clips with descriptive captions. When processing this data, the model breaks it down into manageable pieces. For video, it looks at individual frames or short clips. For audio, it analyzes spectrographic representations or raw waveforms. By mapping these units into a shared latent space, a mathematical environment where text and media can speak the same language, the model gains the ability to perform fine-grained matching. Think of a search query like, "a person laughing in the rain." Instead of forcing the model to create a single, simplified summary of the entire video, a mechanism known as late interaction allows the system to be much more precise. It decomposes your search into specific concepts and scans the media to find exactly where the rain appears visually and where the laughing sounds occur in the audio. By matching these specific tokens to the relevant segments, the system provides accurate results without losing the rich detail of the original media. Bridging the gap between languages is one of the most critical challenges in modern information retrieval. Imagine a user searching in English for a topic that is only documented in Japanese or French. How can a system possibly connect the two? The secret lies in language-agnostic embeddings. To achieve this, we use powerful multilingual encoder models like emBERT or XLM Roberta as our foundation. These models are specially trained to map synonymous phrases from different languages into the exact same positions within a shared vector space. Because of this alignment, the system no longer sees language as a barrier. When an English query token is compared against a French document token, the process functions just as it would in a single language. By calculating the dot product of these vectors, essentially measuring the angle between them, the model can determine semantic similarity regardless of the original language. Ultimately, this allows us to perform seamless, cross-lingual retrieval. The entire process becomes language agnostic, ensuring that a relevant answer is always within reach, no matter what language it was written in. To build an omnimodal late interaction system, we need an architecture that balances high-level intelligence with real-world efficiency. At the heart of this is the concept of a shared latent space. Think of this as a universal translator for data. Whether the input is a block of text, an audio clip, or a video file, it passes through specialized encoders that project all that diverse information into a single common mathematical space. By aligning everything in this shared coordinate system, the model can finally understand the relationships between different types of media. The real power of this architecture, however, lies in how it handles scale. Because this is a late interaction system, we don't have to process everything at the last second. Instead, we pre-compute and store embeddings for our entire collection of media. When a user sends in a query, the system performs a rapid vector search to pull the most relevant candidates. Once it has those, it applies a MaxSim calculation, a way of measuring the maximum similarity between the components of the query and the retrieved items. By delaying this interaction until the final step, the system stays incredibly fast. It allows us to search across millions of diverse media files without the performance bottlenecks you'd expect from such a complex task. The integration of omnimodal and multilingual capabilities is fundamentally changing how we navigate the world's digital archives. By breaking down language barriers and blending different types of media, These systems make information more reachable than ever before. Think about multimedia search engines. Instead of relying on a video's title to find what you need, you can use natural language to search the content itself. You could pinpoint the exact second a specific topic is discussed in a lecture or news clip, making vast libraries instantly searchable. This also powers global knowledge discovery. Imagine an organization with offices around the world. A team member can search through internal documentation in English and pull up technical manuals written in German or Japanese, all without the need for manual translation. Because the system is trained on aligned multilingual data, the language of the query no longer limits the scope of the discovery. Perhaps most importantly, these advancements serve as vital accessibility tools. They empower visually or hearing-impaired users to engage with audio and video content through text-based queries, significantly lowering the barriers to information and fostering a more inclusive digital experience. By combining the precision of late interaction with the breadth of multimodal and multilingual training, we are building a more unified, accessible, and truly global information ecosystem.